Thank you for the introduction. I'd like to thank the organizers for giving me this platform to speak. I submitted the proposal. And the next day I thought, oh, there's no way they're going to want to hear that. No one's going to care. And then they accepted me. It's like, oh, no one's going to come. So thank all of you as well for being here. There are plenty of other interesting talks going on right now. I think I personally would be at visualizing machine learning modules in Jupyter notebooks if I wasn't here, but I appreciate that all of you came here. It's also important that I thank a couple people who helped me with this work. I need to thank my department head, who was hugely supportive of integrating more computer science into our program. I need to thank the head of our computer science program, who's been immensely valuable for helping me think about how to teach programming in a way that's maybe not what it was 20 years ago. And I'd also like to thank the New York City Data Science Academy. I took some classes through their program, and they were the ones who really exposed me to the impact Jupyter Notebook can have to teach math and computer science. So thanks to all of those people who helped get me here. I teach at Trinity High School. Like my disclaimer says, it's a very small, exclusive high school about 2 miles northwest of here at 91st and Columbus. So it's just a quick trip down on the subway to speak. As I go through what it is we're doing and trying to do with these notebooks, I completely acknowledge the amount of resources and privilege that make it all possible. And I don't pretend that you could just export this to any other high school and it would work the same. Like I think I'm in a unique position to be able to do a lot of work, but I think some of the things I'm going to talk about can carry over to a lot of other high schools. My background is in pure math. I went to math grad school, studied algebraic topology for 6 years. As I graduated, I saw a pretty rough academic market, that people beating themselves up to get into 1 year visiting assistant professorships here or there, applying, trying to do research. And then I connected with the independent high school scene, and it's been incredible. Going into my 6th year at Trinity, I have small classes, I have motivated students, and I get to teach a range of topics from freshman math to linear algebra and cryptography. But there's just a ton of opportunity that I've been afforded at Trinity. Okay. So a couple notes that sort of inspired some of this work. A couple notes about maybe the state of computer science education in America right now. Some facts, for whatever facts are worth in the climate we live in right now. But just a couple observations from some studies that have been done on computer science and education. First one speaks for itself. 40% of schools offer computer science with programming. Seems woefully low, a number that surprised me. But I know the high school I graduated from in upstate New York didn't actually offer computer science. When I wanted to take computer science electives there after moving to upstate New York, they put me in a residential electronics class where I was hardwiring and soldering because that was the closest to computers. So I sort of get it. I was surprised by the next one. If I were to ask you what 4 states in America are require that every high school offer a computer science course, maybe you get Texas. It's a pretty big pusher for a lot of education trends, but probably not West Virginia, Arkansas, or Virginia. And that was 2017. Since then, I would imagine maybe the number of the states requiring it have changed a little bit. A number of states also leave it up to individual districts to require. Maybe this district wants to require comp sci, maybe this one doesn't, which is also a valid way to do it, given each district will be maybe more familiar with the resources and requirements they can make. We note that 23 states and DC require it to fulfill a core graduation requirement. And this is a big deal because high school students often are just, what do I need to do to graduate? Maybe what do I need to do to get into college? And if it doesn't fit into one of those 2 buckets, it's probably not going to happen. And just a little note about where the public support is for this. 50% of Americans rank computer science as one of the most important subjects to study. 75% said more important than a foreign language. Like, I'm not here to say teaching computer science is more important than teaching foreign language. I think that is also a unique, creative, incredible experience that math, computer science, and science don't compare to. but it's interesting to note that there is at least the public support. Nothing happens in education without some amount of public support to overcome the inevitable backlash when the education's different than maybe what someone was used to. So in thinking about this, and thinking about how do we get students to take computer science even once it's offered, I get back to maybe the note on the previous slide about graduation requirements and courses. At Trinity, our students take 6 academics per year, up to 6. Many take 5, some take 4. And of those 6 academics they're taking, they need 4 years of English, so one of the 6 English every year. 4 years of math, one of them science. So right away, half the courses are fulfilled. Their modern language requirement, their history requirement. So now there's just room for one academic course. Maybe a student wants to take another foreign language. Maybe a student wants to take a math elective. Maybe a student wants to take an English elective. Between all of these things, we've also got to figure out how do we fit computer science into this student's schedule. And then I also note, as maybe something that applies more to schools in public schools, is the challenge of negotiating computer science standards, computer science credentialing processes. Again, I'm lucky I teach at an independent school. We kind of make it up as we go. It sounds interesting, cool, do it, make it happen, and create rewarding experiences as you can. So that's also a big challenge for the public sector, is how do you manage it all? So a couple other notes that probably aren't going to be a huge surprise to anyone in the audience. Of the AP CSA, so there are 2 different AP computer science tests. The CSA is computer science with Java, and the other one is the comp sci principle. So it'll get more into maybe some of the abstract components of programming without hemming down a specific language. Only 22% of the test takers were female. This observation that women who try AP Comp Sci in high school are 10 times more likely to major in it in college. And then a 2017 Microsoft survey that was done in Europe that argued young women are not getting enough practical hands-on experience with STEM subjects. And there's a whole body of evidence for why this is. This is not a problem I'm even going to pretend that I can solve in any small way. What I'm trying to do is just scratch the surface and help a couple students have a little bit better experience. And so one of our observations is that because computer science doesn't always satisfy a graduation requirement, because it's an elective, you end up with a very self-selected group of students. Who wants to take it, who's been exposed to it, who knows what it is, who thinks they're going to be able to do it. And so the big push for this project is just how do we combat the self-selectiveness of computer science? And our idea was, well, let's just teach it through math. We're going to integrate some computer science into the math curriculum. We're going to bring Jupyter notebooks into the math class rather than wait until someone takes a computer science program class to be exposed to it. As I said on the original slide, when I said Jupyter for every high school student, I only meant the 127 in last year's 9th grade class. That was the first year we did it. Last summer, the department head said to me, hey, make this happen. And so we wrote a couple projects over the year so that every 9th grader would see some Python programming, in particular with Jupyter Notebook. This year, we're going to redo that in 9th grade, and we're going to expand it to 10th grade, and hopefully this becomes a track that follows our students and just lives as a 4-year program in our math curriculum. So here's what I'm trying to do and work with my department mates to do within our program. Again, this is maybe a question that I can answer differently than some public schools, but the question of, is there room? When you talk to a lot of teachers about can they do new things, can they, oh, you're trapped, nope. Can they do new things, can they bring things into the classroom? The first response you always get is, I have to cover so much for my tests. You have tests at the end of the year that are going to cover specific topics, and you have to make sure your students are prepared for those tests. Another huge luxury I have at an independent school is we don't do the New York Standard tests. My students don't take the Regents test. I don't have to worry about what their scores are. I'm not in fear of whether or not I'm going to get to come back on some type of suspension or a probationary period because some students didn't do particularly well. I get our AP scores, I get to see what those are, but it doesn't really impact my reviews, and I don't use it a whole lot to think about or to evaluate the job I'm doing in the classroom. But the big shift in math ed over the past maybe 5+ years has been this thing called inquiry-based learning. How do we get students to ask questions? What are things students should be discovering? We're moving away from the model where I lecture at a board, I have you write down theorems, you do 20 problems that are similar to that, then you work on 20 more problems that are slightly harder, you work on another set of problems that are a little harder still, and then you take a test that covers exactly those problems. We're trying to sort of move away from that model in ways we understand maybe how the brain works a little better, how we understand education a little better, and incorporate more best practice. So what is inquiry-based learning, or what are the 4 steps? Essentially, first one is, should be sort of an obvious thing in education. How do you motivate people to ask questions? How do you generate curiosity? That's far and away the most important thing we do. How do we get students that are curious and interested? And then we let them loose, research it. A different reality is the internet is available now. My students can Google anything. They can come in with unusual theorems. They can come in with unusual problems that they've seen, they've read about on the internet. They need to make sense of it. I need to be able to handle students who aren't familiar with that as it's coming in from different directions. You just have a lot of different things coming into the classroom now than maybe you did 20, 30 years ago. Maybe the next big part is asking students to present their findings. We do a lot of discussion in our math classes. If you came to one of my classes, you might think you were in a history or English class, given how much students are talking, discussing, sharing ideas. They put up problems, they present solutions, they ask their classmates what they think, they hypothesize, well, how might we do it differently in another problem? And then the most important step is that reflection. We've gone through all of that interesting, beautiful work, but now let's make sure we sort of connect the dots pedagogically. Think about what you did, think about what you've learned, and make sure you've mastered that. The reflection step is where maybe what people used to imagine as teaching might happen. Okay, we talked about this idea, we looked at these problems, and now I'm going to connect it maybe the way I might have done in a lecture. Tie everything together, present terminology, give them language for what they're thinking about, and help them really not close up the idea, but come to a good place. So it's my experience that given we're trying to do all of that in math, there's plenty of room to fit computer science with that. How often do you think about a question, something you'd like to do with your code, something you'd like to try and do for a project? Maybe you Google what's available, you find Quora, you find Stack Exchange, you find something there that you'd like to work with, you figure out if it works or not. If you have the time, maybe you reflect on what it was. Otherwise, maybe you just acknowledge you're done and you move on and start the process over. So it seems to me that if I can spark a little bit of curiosity with computer science, then even just let the kids loose on the internet to think about what it is they can do, they'll have a great time and they'll get far. So how did I do it? We used Chromebooks. It's a cheap computer, not cheap, it's $130. Again, back to, for us, we're able to have carts of Chromebooks available. We use them across departments. History teachers, English teachers will bring them in on essay writing days, have the kid write it up on the Google Drive, submit it, and they don't have to worry about what's being done at home. I use the web-based Jupyter notebook, jupyter.org.try, and that have them upload it. I'll pre-write the project ahead of class. I'll email it. They can download it, upload it, and do everything from the web. That's a huge advantage for us. I would love it if all of my students had Anaconda installed with all of the packages and everything up to date, but it isn't always the reality. I would love it if I could just email them ahead of time and say, hey, install this. And you would think the young kids of today, they're so much more tech savvy than we are. But you ask them to install some software, or you ask them to download and upload something, and they just, what? I don't understand it. I can't resolve that, but oh well. So to integrate computer science, we've got Jupyter Notebook and we've got Python. Python struck me as the easy choice for an introductory language. The syntax is great, it's clean, it's a professionally used language. There's just a lot of upside to using Python. The biggest thing I think is that it's readable. You can read Python and have a pretty good sense of what the code's gonna do. And so for all of that, I decided to try Python with them. So a bit of a look to what we do in math, and sort of we'll figure out where various Jupyter Notebook projects fit into this. In talking about inquiry-based math and what that means, we've gone to an integrated curriculum rather than maybe the algebra, geometry, algebra 2 that many of us had growing up. In the 9th grade, we do integrated algebra and geometry. In the 10th grade, we do a bit more of that. So over 9th and 10th grade, you've probably learned most of what you're familiar with in a traditional algebra, geometry, algebra 2 curriculum. We've just sort of chopped it all up, moved things around, and done a little bit of both all at the same time. The big mover in 9th grade that we really are glad we introduced is vectors. Our 9th graders see vectors, they have a sense of what you can do with vectors, and then now that we're also teaching physics in the 9th grade, that helps them in the physics class as well. Our 11th grade on paper looks like a fairly traditional pre-calculus course. We'll get through all the functions. We do this thing that I call Introduction to Infinity, but it's limits, it's series and sequences, it's all of these other things that aren't just graphing or modeling with a peculiar new function. And then in the 12th grade, we have 3 options: calculus at 3 different levels, we have a statistics course, and then occasionally we offer an elective called Advanced Topics in Math. Last year, that's the one I did linear algebra, group theory, and cryptography with. It was a lot of fun, but maybe not the target audience for most of this work that I'm trying to do by exposing all of the students to Python. Though even in that class, I still end up with students who have never seen programming. Bright, hardworking, brilliant math students who just have never touched a computer program. So it's still fun to introduce that in there as well. So what did we do in the 9th grade? Our 9th grade class, the students joke, is essentially all triangles all year. We start out with congruence, we look at properties of triangles, we look at how to prove shapes are congruent using triangles. Once we have a sense of what congruence is, we talk about how it is you get congruent things. So then that shifts us into transformations, rotations, reflections, and all of these things that now we're motivated by congruence. After there, we go to similarity, which is again about triangles. Let's talk about how triangles are similar, how you can prove they're similar. So the natural choice to me for how to integrate some Jupyter Notebook was with triangles. So our first project, I aimed to introduce variables, mathematical operations, if, elif, else, a little bit of logic with triangles, as well as the print command. And variables are fun to talk about with the kids. The difference between x equals 2 and 2 equals x. In math, we treat those things similarly, right? Equals is reflexive, whatever. You go either way with it, totally fine. But in computer programming, this is a big deal. Or x equals 2 versus x equals 2. You're asking different things. And as frustrating as it is when I forget which one I'm using, and I forget that second equals sign, I still understand and appreciate that it's there. And I think most of them sort of were able to develop a sense between, are we saying this is equal to that, or are we asking if it's equal to that? And how that's reflected in the code. So our first project was just using the triangle inequality along with some if statements to check if 3 numbers can be the sides of a triangle or not. Create a little if statement: if x minus y greater than z, or x plus y and x plus y less than z, we get a triangle. Else, print something else, and then within that, okay, well, if you know it's a triangle, can you check if it's a right triangle? And then to get them to think through that, to try and get them to figure out how to figure out which is the biggest side without maybe just introducing some maximum function right off the bat, just to work a little bit of that logic into their thinking. We often like to take credit in math as teaching logical thinking, but I think coding gets at it much more rigorously. Specifically, does it do exactly what you thought it would do or not? The partial credit in coding is very different. Did it run or not? Did it kind of do what you wanted or not? And so I've really enjoyed using it to get them to think more about logic. The second project was just to take all of that work we'd done in the first project and then convert it to a function. How can we define functions now? And when I say project one, that was probably 80 minutes of class time, 80 to 90 minutes of class time to get them to work through all of that with preloaded Jupyter notebooks. I like the notebook because I can have the syntax there, I can ask them to try it, and then redo it with some of the syntax I've already given them. Functions was a shorter one, just one day to convert that and come up with some new functions, talk about how variables work inside functions. And I'm excited for project 2 to actually pay dividends later when we define a function in end of 10th grade, 11th grade, right? This important idea that there can only be one output. Now that they've seen and programmed with functions, it should be clear why that is. And then the last project we did sort of at the end of the year was loops and getting at range. Getting at for loops, getting at peculiarities of counting, getting at while, introducing them to infinite loops. And it's pretty fun because a lot of them will sort of ask the questions about it. It's when they're working through these workbooks, they just generate, oh, what happens if you remove them? And it's really easy to say, oh, just remove that command, see what it does. You won't break anything, like it's going to be fine. And just maybe the increased amount of risk they would take as they work through the third project. So an interesting question has to be, well, how did it go? Did it work? Did it not work? One thing I wasn't actually expecting is and this will come up again in a future slide for things we need to address, is the reluctance of some of my colleagues to lead a class through something as simple as if statements. There are 10 of us in the math department. I would say 5 of us probably have some coding background, but the other 5 maybe have never seen it. So send the workbook out a couple weeks in advance. Hey, work through this, tell me how it goes, and think about how you would lead a class. Oh, I can't do that, I'm gonna need you to come in. It's like, well, fine, but what's the message we're sending to the kids there? That you don't need me to come in, come on, you can do it. So that's a continued goal, is building their confidence in that. But there was one note that I was really, really happy with, and I had to throw it into this slide, is we had a student, in particular a female student, we asked after one of the classes to reflect on how it went, and she said exactly this. I did programming at a summer camp, and it seemed really hard, but this was pretty easy and kind of fun. And I just melted. It was like, yes, it worked, I did my job, I get those teaching feel-goods. It was absolutely, absolutely fantastic. I'm very, very appreciative that she said that. So we did it in the 9th grade. What do we do next? Obviously, as I said earlier, we want this to be a 4-year strand. We want a little bit of it to show up every year. Every year we'll build on what we've done. We'll make it a bigger program. I'll introduce more of my colleagues to programming. So this is going to be my next year project. I've moved from our 9th grade team to the 10th grade team, in particular to do this. And so our 10th grade gets into a lot of 2D, 3-dimensional geometry. We explore vectors more, we introduce dot product. So I'm excited to see what I can do with NumPy. See if I can get them using some matrices. See if I can introduce them to the idea of packages. Oh, maybe you're not familiar or you don't know how Python's going to do something, but someone's probably figured it out. Most of your questions are natural questions that people would want to ask and things they'd want to do. So let's go back to that step of research what's out there. And then additionally, I'd like to do transformations with the kids. I think this will be a fun way to get at functions, to really use matrices, to use some of that trig they've been developing. Right triangle trig, fine, but getting them to rotate things will be a lot of fun. And I suspect by the end of that, I'll be able to teach them how to rotate images. Upload an image file, apply a transformation to it, and then look, oh, you've by hand rotated some image. One of my summer projects has been learning homography. I don't know if anyone's familiar with 3D visualization and using homography in a lot of linear algebra. And our honors track actually gets into a bit headier math, and I think I might be able to explore some of that, which could potentially have interesting AR applications, is getting them to do a little bit of AR and understand the way 3D geometry works. So conceivably, this will be 2 years down the line. When we get these current sophomores are then going to be 11th graders, and they're doing analyzing all those functions. I'll try and get them to use matplotlib, do a little bit of graphing, as well as recursion. This past year, I had sort of a weird reflection. We teach recursion in math, but we have them do it by hand. Here you go, here's this sequence. Use recursion to find the third term. And it's like, well, it doesn't seem like that's really grasping at the power of recursion to just by hand do 2 or 3. So it almost seems foolish to teach it without computer science along the way. So I'm excited for all of the things we're going to do with recursion. One of my favorite recursive problems is asking someone to write a program that outputs the steps for the towers of Hanoi problem, where you've got to move the tower from one pillar to one of another 2 pillars. And there's certainly a lot of ways to do this problem, but there are some very, very elegant ways that use recursion and solve it very simply. 12th grade is, I think, where we're going to be able to do a lot of work with this, in particular statistics. Now, there are some that argue that, and Art Benjamin has a great TED talk on this, that statistics should be the culmination of a high school experience, not calculus, that we should move past calculus as king. And I don't know either way, and we're integrating more stats into our core curriculum, but as indicated in the graphic there, it feels a bit foolish to me that we teach statistics with a graphing calculator. Like, I don't think data scientists go into the job, whip out their TI-84, connect it via USB to the computer so they could import some small amount of data onto this calculator and then run statistics. Like, it just doesn't seem realistic to me. But I think now that they've got these Jupyter notebooks, they can do pretty high-level professional statistics. And the goal would be to introduce them to pandas, to SciPy, and scikit-learn. We're in the process of moving our AP Stats class off the calculator right now. So this one, I don't even think we'll need to wait until the current sophomores track through to 12th grade. And the argument we had was R versus Python. Do we use R? Do we use Python? One of our statistics teacher has an R background from maybe 20, 30 years ago, and it certainly makes sense. R's a great tool, but Python seems to tie in better with everything else we're doing. So I think I won that battle, but I won it pending providing a lot of support to her Python development. But I'm excited to do that. And then calculus. What is calculus? Well, we study the rates at which things change and how much they've changed. And a really useful feature in calculus is that we can approximate things nicely. We do a lot of approximation with calculus, and this seems like a great way to integrate a whole unit that's just coding. We usually look at Newton's method, a way to find zeros iteratively. We'll compare it to the bisection method. We can compare which runs faster and why. We can acknowledge that maybe we're using more information in one algorithm than the other, and that's why it's able to run faster. But I think a computational calculus class will be pretty helpful for our students. So conceivably, student goes through our math program 4 years. It's not to say they're going to be professionals, but they'll in some sense have seen all of these topics just by taking math for 4 years. And they'll be positioned well to go on to take whatever computer science, to think about what types of questions they can ask and answer. Students that aren't even going into STEM fields, students that want to go into sociology and want to be able to do some type of statistics, right? Statistics is a hugely applicable field, and now our students can take that into other domains. So like I said earlier, what's maybe the biggest hurdle? Training more teachers. How do we get more teachers that are comfortable with programming? My summer sort of professional development spin has been working at NYU to learn robotics, and that's been pretty neat. But among what you would imagine is a somewhat self-selected group, we had teachers who have never seen computer programming before. And we're trying to sort of hunker down in this primitive basic and try and program robotics and just have no sense of what a for loop is, how do we want this to run, how do we control that. So I think the biggest push has to be, let's train more teachers, regardless of whether they're CS teachers or not, just in the elements of programming. One of my colleagues from the NYU program that just wrapped up last week said, I still don't know what MATLAB is, other than it ran for 2 days on my home computer and then did nothing. And I was like, oh no, oh no, we've got to beat that. So most of what I've done is used the math content to drive some computer science. And I think my end goal would be to flip it. Here's some math you want to explore, some math you want to think about, so use a little bit of computer science to explore the math. And this problem came up in my topics class. Maybe you've heard of the postage stamp or the chicken McNugget problem. If you've got boxes of 3 McNuggets and boxes of 5 McNuggets, what's the largest amount of McNuggets that's not possible with those 2 combinations? And this generalizes it to more than 2 boxes of McNuggets. And the students brute forced it, and they found it wasn't running fast enough to get an answer, that it was going to take years. So then it became, well, let's use math to figure out how to get at these answers more elegantly. And so that was sort of one of the first times where we were able to sort of flip it and try and solve a math problem that we needed to answer after asking it as a computer science program. 2 other sort of big pipe dreams. Not going to get too soon, but Jupyter Notebook can be used to control the pins on the Raspberry Pi with GPIO. So now we can integrate some circuitry and look at how the logic is working in those circuits, as well as some robotics with Gazebo and ROS. So thank you all for staying with me. Are there any questions? Oh, I've got one in the back. Get in the mic. Uh-oh.
Speak loudly.
Yeah, you might be able to buy just. Yeah. Yes. Yeah. We've certainly there's a bunch of we've started to look at how do we integrate. So the question was, am I familiar with the book Doing Math with Python? And yes, we've got that one. There's also a great free stats book that integrates Python that we're going to look to integrate just to give the kids more resources. I imagine it becoming like some type of resource list. Look at these books, but for sure. Thank you.
Well, another similar book is Hacking Math Class with Python, if you've heard of that one.
Hacking?
Yes, Hacking Math Class with Python. He also has a website as well, which will correlate with that book.
Sweet, thank you. I'll write that down. One of the things I was excited about to speak here is that I would have a room with industry professionals that could share much more of the tools they've encountered than I would be able to find quickly. Yes.
Hi. When the students are going through it, one of the things that the notebooks really make easy is visualization and interactivity. Are you seeing that reflected in your classes?
So, as per interactivity, not in the sense where they're creating like interactive graphical things. I am seeing a little bit of interactivity as per, well, what happens when I change this? How do I modify this? What happens if I tweak this? What happens to all of this? Definitely. A lot of questions around that. That was how we sort of stumbled onto infinite loops. Well, what happens if you remove this? And then, well, what's happening and why? And then that's been a great way to get them to ask some questions. Is just play around with it and see what you get. I've got one more, then we'll come back.
I've always kind of thought that the math area would be the ideal match for computer science in the high school level. Have there been other, you mentioned physics briefly, have there been other fields that have been sort of curious about what you're doing and thinking, oh, maybe I could model or simulate some physics kind of stuff? Or
So for sure we've seen science slowly take on more. Our advanced physics is all mechanics, and they did a number of Python projects this year. Another peculiar thing, maybe this goes into a different realm of comp sci, is our history program had the students create board games, and they had to 3D print the pieces. So that was really neat to see. Then those students had to open, I think we use AutoCAD, maybe? OpenSCAD to create stuff and get at that. So we are seeing it in some departments. The one thing that's going to be big is we do these weekly teacher presentations to other teachers. And so I think a couple of us are going to have to figure out, how do we present programming to the population more broadly? English teachers, history teachers. I would love to get to where, say I'm doing text analysis with some of the English teachers. One of my friends, huge Shakespeare buff, let's take some Shakespeare and let's look at what's in the text. So let's analyze it. Anytime you read about this analysis that they find, this work really looks just like this work. Well, let's show them how that happens. We introduced vectors in the math curriculum in 9th grade, so now we can do some word-to-vec stuff and look at what's going on there to do some text analysis.
I can ask. Hi. I was wondering if all this material is open somewhere. Is there a way that we can contribute to? I think in this whole thing, to spread it out, and because I feel like there are a lot of people that will be really grateful if this will be out there and
Totally.
can reuse it.
So I would love to get it all out there. I suppose the next step for me then is to make a personal website that's got it all on there. I don't know that institutionally we have like the Trinity Math website where you would see all of this, but I am happy to share.
But we wouldn't be able to find it, right?
Totally. I'll make that note. GitHub's certainly the right way to look at it. And I think that is also a great segue into what the next presentation is going to be about. Presentation of a group from Canada that's using GitHub to do this exact thing. So if you're interested in that, by all means, stay around and listen to what they're going to have to talk about. They're doing something very similar, exactly in that vein.
Extremely interesting. Going back to your math curriculum, one of the things that we find really good when we're teaching Python to adults is the quick response that you can get, right? You can get a graph right away and so on. I found it interesting, though, that you're pushing the matplotlib and the pandas until much later, whereas that's kind of my intro to stuff. Is just like, if you get these things down quickly, you can start making really graphs, and people get excited by that. So the question is twofold: is what informed that choice? And the second thing is, as you're looking at how you teach math, what ideas are you getting about changing the order of the curriculum, the way you teach math, given that the kids now have these tools that kind of bring it alive in a completely different way?
So as per the first question of ordering of tools, our computer science head has been thinking for a long time recently about how to teach programming, what's important, what do they need to get out of it. And so I think he's, in some sense, a little reluctant to hand over too much too quickly. For whatever reason, that's where he's at. And so the thing that just made the most sense to us at the time was, let's start using some logic. To the graphing end, something that has changed the way I teach is Desmos, an online graphing utility that's just mind-blowingly fun to play around with. Math probably is one of the least doodling or experimental subjects you'll do. You can doodle, you can do art. In science, you can have questions, you can do experiments. But in math, how do you create hypotheses and answer them? And Desmos has been a game changer there. It's not Python, but there's still a little bit of programming, solving for variables, and getting at that very, very visually satisfying component of seeing it. So for sure there, maybe as we do more graphing, we'll decide it does make sense to push the matplotlib and some of that down. Like, I could certainly see the argument for that. It just happened we didn't yet. Also our 9th grade course is very proof-based anyways, so the logic fit, I think, a little bit better, but it's also coordinate geometry, so I could see it going both ways.
I just wanted to share a vignette. I heard from a colleague about a similar experiment that took place associated with the science fair in Chicago. So a group of students were interested in data science, and they submitted a data science project in Chicago that was reviewing data associated with the profiling of arrestees. So this was a group of students from a rather poor high school who were African American, who then did a data science project using Jupyter and pandas to study racial profiling in Chicago in the context of a science fair. And so I think there's this really interesting twist there where it's a math class, but there's actually an engagement in digital citizenship and a transformation in the discussion around this politically volatile issue by students who are doing something in a science fair. And I just think this overlap of these themes is really quite exciting.
Totally. That's a great observation, great story. One of those things we're looking at more, particularly given the amount of privilege we have as an institution, is how do we integrate more social justice into our program? For English and history, I think that's an easy question to answer. For math, I think it's a harder one at times. And examples just like that, with the economics, with the statistics, and getting at analyzing and asking about issues like that.
Please give a round of applause to Rod Newman.
Thank you all. Thank you all very much for coming.